So in the previous discussion, we have learned that any periodic function can be expressed as a sum of sine and cosine terms, right? Using Fourier series. Now, however, an important question actually arises that how much of these sine and cosine component is present in the function? The answer is given by Fourier coefficients. So Fourier coefficients are the constant that determine the amplitude of each harmonic present in the series. In other words, they actually tell us how strongly each sine and cosine term contributes to reconstructing the original function. Alright, these coefficients are, how are they obtained? We'll learn in this video. These coefficients are actually obtained using integration, okay, and they are essentially they actually measure the contribution of each harmonic, like what is the contribution of sine, what is the contribution of cos term in the function. So in this lecture we'll actually learn how to calculate these coefficients and understand their physical and mathematical significance. All right, so let us now move into the calculation part. So we know that f of x can be expressed as f of x is equals to a naught by 2 plus summation over n um, an cos nx plus bn sin nx, and the bracket ends here. So let us define f of x in the interval. For example, let us take an example. So let us define f of x in the interval 0 to 2 pi. All right, so what does this means? That 0 to 2 pi is the interval in which f of x is defined. All right, then what happens? Then we can say we can integrate this entire equation, this entire equation starting from here and ending here, from 0 to 2 pi. All right, so integration 0 to 2 pi f of x dx is equals to integration 0 to 2 pi a naught by 2 dx plus summation over n a n integration 0 to 2 pi cos nx dx plus bn 0 to 2 pi sin nx dx. All right, so now what we know that integration. Now let us look into the terms one by one. All right, so let us change the color. So the first term on the left hand side is this, right? Just highlight it. This is the first term on the left hand side, right? So integration 0 to 2 pi f of x dx is equals to, now the first term on the right hand side is this one, right? Second term on the right hand side is this one, and third term on the right hand side is this one. All right, so if we look into it now, left hand side integration 0 to 2 pi f of x dx changes to a naught by 2 what will be a? Why does a naught by 2 come out of integration? Because a naught is a constant, 2 is also a constant, so constants always come out of the integration. So a naught by 2 integration dx is x, and we put the limit 0 to 2 pi because this is a definite integral, right? Plus, look into this term. This term has got cos theta in it, right? Cos x, cos nx dx. So we know integration of cos nx from 0 to 2 pi is nothing but 0, right? Because why is it 0? Because we know over a complete period the cos and sin theta gives us 0 as integration. Why? Because the positive part and the negative part, I mean the positive area and the negative area of cos theta and sin theta basically cancels out, and the integral ultimately gives out 0. Alright. So this an term also gives us 0. And what about the bn term? Also gives us 0 because bn has sin theta in it and an has cos theta in it. So cos x dx or cos nx dx integration integrated over 0 to 2 pi, that is over a complete cycle or complete period, gives us 0. Similarly, sin nx dx integrated over 0 to 2 pi, that is over a complete period, gives us 0 because these are because their like positive area and negative area of their waves, like of their curves or waves, gives us 0, right, over a complete period. Now, so what happens is, what this equation changes into is, we can say that integration 0 to 2 pi f of x dx is equals to a naught by 2 and 2 pi, because x, if we put the upper limit minus lower limit, that is 2 pi minus 0 is 2 pi, right? So what is our aim? Our aim is to find a naught, right? We are here to find out the Fourier coefficients in this video lecture, right? So a naught is the first Fourier coefficient, then comes an and then comes bn. So for finding a naught, let us keep a naught on the left hand side, and let us we can see that, sorry, these two and this two will cancel each other. So for finding a naught, what we'll do is we'll keep the a naught on the left hand side, and we'll transfer the everything like rest of it into the right hand side, right? So what will happen is 1 by 2 pi, sorry, 1 by pi, because we have already cancelled it 2. 1 by pi integration 0 to 2 pi f of x dx. Alright, so a naught comes out to be this. What is this? This is 1 by pi integration 0 to 2 pi f of x dx is what is a naught. A naught being the first Fourier constant. Alright. Now similarly, we'll look for an and bn as well. Alright. Now let us try finding out an and bn, right? We have basically three constants, a naught, an and bn. So for finding out an, we will write the same statement again, but this time we'll multiply the entire equation, both left hand side and right hand side, with cos mx term. Alright, so if we multiply something on both hand side, like both left hand side and right hand side of an equation, then the equation doesn't change, right? So keeping this in mind, let us multiply cos mx on the left hand side, similarly cos mx on the right hand side, and this cos mx will appear in every term of the right hand side. So summation over n, an integration 0 to 2 pi cos nx into cos, sorry, I mean it becomes very difficult to write in this way. Cos mx, cos nx was earlier present in the equation. All right, we have just multiplied cos mx to it. You get the difference between m and n. Similarly for bn, we have bn integration 0 to 2 pi. Sin nx was earlier there in the integration. We are just multiplying a cos mx to it. All right, dx. We close the bracket here. So how will this behave? Now we know that, okay, let us first write the left hand side of the equation. Left hand side being 0 to 2 pi. I am just changing colors so that you get to know that the entire thing in the pink was the first equation. Again we'll write the next we'll write that equation, but after some calculation on with this violet color. All right, so f of x cos mx dx is equals to the first term on the right hand side, if you remember, contains what? Contains a naught. All right, cos mx, a naught by 2 integration 0 to 2 pi cos mx dx, right? If you remember, this was the term, this was the term, right? Isn't it? So this basically contains what? A naught by 2 integration 0 to 2 pi cos mx dx, and we know integration 0 to 2 pi, that is integration over a complete cycle of cos theta, gives us 0, because the plus area and the minus area of the curve, of the cos curve, ultimately gives us 0 over an entire cycle, because the plus and the minus cancels out, giving us 0. So the first term on the right hand side turns out to be, turns out to be 0. All right, with a plus sign. Now comes the second term, right? So for the second term, if you can see that the second term contains cos nx and cos mx integrated over the interval 0 to 2 pi, right? Now so to evaluate the second part, like the second term, let us first break it down. I'll do it in a different color because this actually needs time to explain. So let me just change the color for the time being. This was violet, right? So now we'll continue with just the second term. Which one is the second term? The second term being this one, a naught integration 0 to 2 pi cos nx cos mx dx. All right, so now what can this term be written into? So we cannot directly evaluate this term, right? So we need an identity. What is our identity? Our identity is anything, like any formula, which breaks down a complicated formula into simpler parts so that it becomes easier for us to calculate. Like when we get stuck in some calculation, we use an identity. We use that we use some identity to simplify and break things down in a less complicated way, so that calculations become easier, right? So this is a different part. Okay, this is not a part of this calculations we were doing till now. We'll now just take up the second term, which is an integration 0 to 2 pi cos nx cos mx dx. All right, and this will break into, what will this break into? Again, we'll use an identity which breaks this into, forget about the a in term. A in being a constant, we'll not look into it right now. We'll just put it as a n, and then this will break into half integration 0 to 2 pi cos m minus n x dx plus half 0 to 2 pi cos m plus n into x dx. Alright, we'll close the bracket. Now from here arises few cases. What are the few cases? For example, case 1. Okay, what is case 1? If m is not equal to n, what will happen, right? So when m is not equal to n, then we can say that m minus n and m plus n, and m plus n will not be equal to 0, right? So we use these result. What happens is, so what happens, like, so we can say that let us put m minus n as k. All right, and what do we know? We know that 0 to 2 pi integration cos kx dx is equals to 0 when k is not equals to 0, and here k is equals to m minus n, right? Similarly, we can also put m plus n is equals to k prime and say that 0 to 2 pi cos k prime x dx is equals to 0 only when k prime is not equals to 0, and we know that neither m plus n nor m minus n is 0 in this case, because m and n are not equal, they are different. Since m and n are not equal and they are different, we can see that both the terms of this integration, like the first term and the second term of the integration, turns out to be 0, because cos kx over 0 to 2 pi gives us 0. K can be m plus n, k can be m minus n, doesn't matter. Alright, so this being the first part. Now let us come to case 2. Let us come to case 2. What is case 2? Case 2 is, what if m and n becomes equal? Alright, m is equal to n. Then what happens? Then the integration term, if you can see that this was the integration term, right? This highlighted part. I'll highlight it once again with yellow. This was the integration. Okay, yellow is being too faint. Okay, blue. So this was the integration, right? This was our original integration. We had used an identity and had broken it into two parts, term 1 and term 2, so that it becomes easy for calculation. Just to make our calculation easier, we are using here identities. All right, so let us come into the second case of this identity, of this integration. What if m and n becomes equal? What will happen? This term will change into an So what will it change into? Cos mx will become cos mx, and cos nx will also become cos mx. So what will be the term in the integration? It will be an, where is it? Yeah. So it will be an integration 0 to 2 pi cos square mx dx. Alright? Isn't it? Yes, it is. So now we know that cos square theta can be written as half of 1 plus cos 2 theta. Haven't like you have must have read it in your earlier classes that cos 2 theta is 2 cos square theta minus 1, right? So just keeping the left hand side terms, moving the left hand side terms into right hand side and right hand side terms into left hand side, we can say that cos square mx, cos square mx, that is cos square theta, can be written as half of 1 plus cos 2 theta, that is 2 mx, isn't it? So now moving into the next part. So what we can say? We can say that integration 0 to 2 pi an over the out of the integration, because an being a constant, cos square mx dx gives us half 0 to 2 pi. What will be this? The 1 will come first, 1 dx plus half integration 0 to 2 pi cos 2 mx dx, isn't it? This was the second term, right? Let me highlight. The first term was 1, isn't it? And the second term was cos 2 mx. So we have put the second term here, cos 2 mx, and put the first term here, 1 dx, isn't it? So now what does the first integral give us? What does the first integral give us? This 1 integration 0 to 2 pi 1 dx. It gives us nothing but half x 0 to 2 pi, isn't it? Because integration of dx gives us x, right? Now, and what about the second integral? Plus, the second integral is integration cos theta d theta over 2 pi, which is 0, because we have said this innumerable times earlier in this video that cos theta and sin theta integrated over a complete integral of 2 pi, they give us 0, because their plus positive part of the sine curve and the cos curve area cancels with the negative part area of the cos curve and sine curve respectively. Alright, so the second term will yield us 0. So what is our integration result? The result is an integration 0 to 2 pi cos square mx dx is equals to half of 2 pi is equals to pi, isn't it? The 2 and 2 gets cancelled off. So now comes our final answer. So rewriting the entire thing, what we can say that integration 0 to 2 pi cos mx cos nx dx is equals to, now arises two paths, pi when m is equals to n, isn't it? And 0 when m is not equals to n, because this is what we got, right? See, we got pi when our case was case 2, this was our case. I'll highlight it best way. Wait, let me change the highlight color to red. Alright, so now look at it. We got pi when our case was m equals to n, right? And we got 0. Where's the 0? So I think this was the one. So we got 0 when our case was m not equal to n, right? So what we can infer, this is what we can infer, right? So this integration, we have missed an a in term. There was a an, right? This integration, okay, let us not write the an term, we'll multiply an with it later on. So this integration of 0 to 2 pi cos mx cos nx dx gives us 0 when m is equal to n, and gives us m when m is not equal to n, and gives us pi when m is equal to n, right? So this in a compact way can be written by Kronecker delta function, which says that integration 0 to 2 pi cos mx into cos nx dx is equals to nothing but pi delta mn, where pi is pi and delta mn is what? I've said this earlier as well. Delta mn is the Kronecker delta function, which gives us 1 when m is equals to n, and 0 when m is not equals to n. Alright, this is the property of a Kronecker delta function. So Kronecker delta function gives us 1 when both its coefficient m and n are equal. It gives us 0 when both its coefficient m and n are unequal. Alright, so similar, this actually what it shows is, this result shows that cosine function of different frequencies are orthogonal over 0 to 2 pi, which is the foundation of Fourier series. We'll later see into this, like look into this. So let us not discuss this now because it will take time. Now let's quickly say in a similar way, I'll not find out bn. So what exactly is an, right? Okay, so we are done. All right, so we'll draw a line here and we'll move into the pink part, this purple part of it. Like we were dealing with this equation, right? This very equation, and we had found that the first term was 0, that is this term gave us 0. We found that this term gave us pi delta mn, right? So we'll add with it, pi delta mn with multiplied with an, because we had a n, right? And a summation sign. Summation is over n. Plus, similarly, let us look into the second integration now. Well, let us move to the next video because it's getting too long.